Next, we're asked to explain why the amplitude changes when the detector is moved, not that way, but that way. All right, well, let's just suppose that at O, the detector is detecting a maximum. So the amplitude is maximum. If we move perpendicular to these lines, if we move perpendicularly away, well, we're still going to be at a maximum. So, but they're telling us that the amplitude is going to change. So it's not, we're not moving from a maximum to a minimum. That can't be it. So why is the amplitude changing? Here you need to recognise that, and I don't know whether maybe even just intuition is the best way to do it here. If you move further away from a wave source, the signal you're detecting is going to get weaker. So that's what's happening, but then why? Well, it's because as a wave spreads out from its source, the energy carried by the wavefront is being spread over a larger and larger area. You're probably familiar with a diagram that looks something like this, and what it's trying to show is that whatever energy was emitted in this direction, well, at this point it's spread over that area, and then if you double the distance away, the area that it's spread over is now this, which is 4 times bigger. So this, remember, is because intensity is the power per unit area. So double the distance away that you go, then you quadruple the area that you spread it out over. And then, because intensity is directly proportional to amplitude squared, if the intensity decreases, so does the amplitude. Okay, so our answer says the intensity and therefore amplitude of a signal decreases the further you move away from the source. For the first mark, this is because the energy or the power is being spread out over a larger and larger area. And now for a third way that the amplitude is changing. So now it's explain why the amplitude of the detected signal decreases to a minimum before increasing again as transmitter A is moved a small distance in the direction AR. So the transmitter A is going to move a small distance in the direction AR. So this transmitter here moving that way. Why is it that the signal decreases from a maximum to a minimum? Well, now we're back to interference patterns again, because we've already said that you get a maximum here when the two waves arrive in phase, and then you get a minimum when the two waves arrive in antiphase, exactly 180 degrees out of phase. Right, but so let's go back to our maximum here. So the two waves, I mean, it looks to be the centre, so let's just say this is the central fringe. These two waves are travelling exactly the same distance to get to O, and that's why we have a path difference of 0 and a maximum. If we now move this one further away, well then now they're not going to arrive in phase anymore. Now they're going to arrive out of phase. So that is why the signal is going to decrease. Now we were told it's going to move a small amount that way, but how much would it need to move to get a minimum? Well, it would need to move a half a wavelength. If it moves a half a wavelength that way, then at that point, this wave is going to have travelled exactly half a wavelength longer than this wave, and then they'll be exactly out of phase. They'll be in antiphase at that point, and they'll completely cancel out. Okay. But what was the small distance about, you might be thinking? Well, a wavelength is 3 centimetres, and so half a wavelength is 1.5 centimetres. So that's what the small distance was about. It's a reference to the fact that we're moving it half a wavelength. Okay, so in answer to this question, for the first mark, when the transmitter has moved half a wavelength away, the two waves will arrive exactly out of phase at O, and this will lead to a minimum. And for the second mark, this distance is therefore 1.5 centimetres, or 1.5 times 10 to the minus 2 metres.